Perfect timing, Sasha. You found the pins just in time. All right. Okay, I'm sorry to do this, little man. Okay. All right. So finally found paper, found my pins, got my microphone set up so that that is upside down. I'm gonna have to go ahead and flip that. Boop. So this should be hopefully right side up. Yes, okay. Not perfect. Camera is at an angle, but hopefully we can make do. All right, so this is the lab. There's a lecture-ish thing that will cover lab 1. All right, what am I looking for? What am I looking for? I am looking for lab 1. Where am I going? Go to course con. Thank you. A cat will never, ever leave well enough alone. Okay, so we got a number of topics going for us with this lab. We have the metric system. We have conversions. We have exponential notation. And we have significant figures. Okay. So let's go ahead and jump in with the metric system. More properly, the imperial system, the system international. Let's me check real quick, make sure sound is coming through. More properly. Yes, sound is coming through. Excellent. Okay. So, the imperial system or the system international. Got a number of what are known as, no, Sasha, I love you, but you're getting in the way. Okay, you got a number of base units. Okay. The way they work is you'll have something like the gram as the unit of mass. Or the... God damn it, cat. Get off the keyboard. All right. I love you, but just stay over there. There you go. There you go. Now you're close enough that I can still pet you. All right. You have the second as the unit of time. You have the meter as the unit of length. And so on. Okay. So, international system, it's abbreviated SI because it was developed by the French. Therefore, it is the system international. Now, the thing is, this system works really, really well because it doesn't restrict itself to a single scale. Okay. So the way we can change that, we have two different ways. The first one is the one that is a little bit easier when it comes to people doing stuff, a little bit easier when it comes to writing, and that is with prefixes. So prefixes go from very, very small to very, very big. So you have N for nano. That is 10 to the negative ninth of something, or 1 over 10 to the ninth, or 1 over 1 billion. So very, very small. Then you have micro. Looks kind of like an M, but the way you do that is you draw a lowercase u, then you give it a straight stem on the other side. That's not what I want. Oh, you can't hear anything? I could hear something when I... Crap. Why? Okay, I'm going to refresh. Me. Okay, the microphone is picking up. Okay, so it's just Morgan can't hear. Okay. All right. Try unmuting your YouTube then, Morgan. Sorry about that. All right. So next up is micro, which is 10 to the negative sixth. followed by milli, just 10 to the negative third. And then you have centi and deci, 10 to the negative second, 10 to the negative first. So as you get closer and closer to the base unit, we start to go in jumps of powers of 10. But getting further away, it doesn't make sense to use those powers of 10 when you get further away. So we start going by powers of 3. So 1/10th, 1/100th, 1/1000th, 1/1,000,000th, 1/1,000,000,000th. Okay. It goes in the other direction as well. Obviously, we want to be able to look at big things too. So starting from the base unit, we have D for deca, as in decade. Oops, you can't see that. Followed by H for heka. It's 10 to the first, 10 to the second. Lowercase k for kilo. That's 10 to the third. Then we have uppercase M for mega. That's 10 to the sixth. That's 1 million. And then we have giga, or giga if you're Doc Brown. Dated reference, I know. That's 10 to the ninth, 1 billion. So these prefixes allow us to go back and forth between different sized units. So for example, we can go from 103 kilometers to 0.103 megameters. Okay. It's just a matter of moving the decimal place the appropriate number of units. Okay. So kilo is 10 to the third, mega is 10 to the sixth. So in order to move from one to the other, we're going from 3 to 6, the decimal place is going to move 3 spaces. It started out, so I can use my multiple colors here. So it started out right here. To go from kilo to mega, we move 3 spaces to the left. And that's how we get from 103 to 0.103. So just remember, when translating from one prefix to another, that going from a smaller unit to a bigger unit, the number is going to get smaller. Bigger unit means a smaller number, and vice versa. So a kilometer is smaller than a megameter. Therefore, the number of kilometers is going to be bigger than the number of megameters. I'm immediately suspicious whenever my cat gets very interested in something. It usually means there's an insect. I don't know what he's freaking out about. I'll let him play. Okay, so they are definitely going to expect you to know how to translate between different sets of prefixes. And they can go from really big to really small, or from a big thing to a bigger thing, or small thing to a smaller thing. It's a matter of looking at, one way of looking at it, I should say, is looking at the exponents. That is the way that works for me, but I am somewhere on the autism spectrum. I'm good at thinking about things in terms of numbers. Maybe for you, it'll be a matter of memorizing. That's just fine. So prefixes is just one way of dealing with the size of numbers. It's a way of acknowledging the fact that we're studying a universe that goes from the very, very, very small to the very, very, very large, both in terms of time and distance and mass and all sorts of things like that. The other way we have of dealing with different sizes is with scientific notation or exponential notation. So exponential notation looks like this. Some number times 10 to an exponent. Okay. So the average distance of the Earth to the Sun is 93 million miles. To put that in exponential notation or scientific notation, you just move the decimal point until you have a number from 1 to 10. So 1, 2, 3, 4, 5, 6, 7. Okay. So our new number is now 9.3 times 10 to the 7th miles. That is the exponential notation or scientific notation of that number. We moved the decimal place 10 to the left. Now, the reason we do this is because when it comes to the measurement, the size of the measurement is different from the value of the measurement. The actual value of our measurement is this guy right here. This right here is just the size, and then this is the unit. Okay. So anytime we make a measurement, those are the three portions of the measurement: the value, the magnitude, and the unit. Okay. And those are different pieces of information, and it is useful to be able to separate the value of the measurement and the size of the measurement. I'm bringing that up now because I think it's helpful for understanding significant figures. We'll get to that later. Now, this also lets us compress very, very small numbers. So, just for example, the nucleus of an atom is about 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 1 meters. All right, so that is the size or the radius of the nucleus of an atom. They are incredibly, ridiculously, absurdly small. And we do the exact same thing for really small numbers as we do for really large numbers. We just move the decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. And that gives us 1 times 10 to the negative 25th meters. So that is scientific or exponential notation. We use exponential notation for two reasons. First, because we don't have to keep on making up prefixes. We have made up prefixes beyond nano and giga. There's, tera and pico and zotta, and they just kept on going. But we don't use those because it's inconvenient to have to memorize a couple dozen prefixes when you can just use this. The other reason is that prefixes are actually fairly convenient for humans, especially when you're going in, jumps of 3. You can have a measurement of 205 kilometers, and you can have another measurement of 10.3 megameters. And as a person, a human being, it's relatively easy to compare those two numbers. You just convert this to 0.205 megameters, and you can see, oh, okay, that's the relative difference in the size between them. But the other advantage to scientific or exponential notation is that it's really a lot easier for computers to work with this. They're very good at chunking information into different segments in the way that I talked about right here: value, size, and unit. So when you're working with, whether it's a spreadsheet or a graphing calculator or anything like that, when you put something in scientific notation, then it would be something like 9.3 E7. And that is how a lot of different computer programs will report 9.3 times 10 to the 7th power, or 93 million. It just gets rid of all those inconvenient and frankly useless, well, not useless, but largely unhelpful zeros. The zeros are just there to show the size or magnitude of the number. And we can get rid of that with, this notation right here. Really useful, and that's what we use it for. Which brings us to significant figures. Okay. Significant figures comes, don't quote me on this, out of information theory. How much information is actually contained in a measurement. And thus the value of the measurement is separate from the magnitude of the measurement. So how to tell if a number is significant. A non-zero number is always going to be significant. That is the simple part. The question comes as to whether or not a zero is significant, because some zeros are only there to show the size of the number. Some are there as part of the value of the measurement. So that is what significant figures are really there to tell us about. Okay. So we talk about three kinds of zeros. They can have names if you really want them to. So there are leading zeros, captive zeros, and trailing zeros. So a leading zero is a zero to the left of the number, or a zero on the left-hand side. So 0.00357. Okay. Those are all leading zeros. And a leading zero is never going to be significant. Okay? A leading zero is only ever there to show that the number is small. Therefore, it's not part of the value of the measurement. Okay? So this has, a non-zero number, a non-zero number, a non-zero number. It has three sig figs, as we call them. Only three significant figures. This, and this, not significant figures. Now, a captive zero is a zero that is located between two significant figures. Okay. So, again, for example, $3,057. Okay. The 3, the 5, and the 7 are all significant. The 0 is located between significant figures, therefore it is going to be significant. So this number has 4 significant figures. So a captive 0 is always significant. Because a captive 0 is always trapped between significant figures. It's always buried in the middle of the number. It's always buried in the middle of the measurement. It's part of the value of the measurement. Okay? So leading zeros are never significant. Captive zeros are always significant. Okay? Because a captive 0 is never there just to show the size or magnitude of the number. Okay, it's just, this is part of the measurement. The measurement goes all the way down to this smallest part of the thing. So technically, these should have values. So this could be grams, and this could be grams. Okay, this thing, whatever it is we're measuring the mass of, it weighs 3,057 grams. The fact is, it could have been 3,157. It could have been 2,957. But it just happened to be 3,057. Even though that's 0, it is a significant 0. It's telling us that it has 0 hundredths of grams. Now, a trailing zero, if you've caught the theme so far, is a zero on the right-hand side of the number. And I'm going to go ahead and cut to the chase on this one. Trailing zeros are sometimes significant. Sometimes they are there to show the size of the number. Sometimes they are part of the value of the measurement. So this is where it can get fairly tricky. So, for example, we take a measurement, 3,200 grams. Okay. Now, it could be that the device we're using isn't particularly sensitive. It can only measure down to the 100s. So it could be that we just don't know what those two zeros are. This mass could be anywhere from like 3,150 to 3,249. Just these are lost in the rounding error. If that's the case, then these zeros are only there to show size, and they're not significant. It could also be the case that our machine does go down to the 1 gram measurement, and it just happened to have measured a zero. So we need a way to distinguish that. And the way we distinguish between trailing zeros being significant or insignificant is going to be by using decimal places. Okay? The presence of a decimal is going to tell you whether or not something is significant. So a trailing zero with a decimal is going to be a significant zero. That means that it's actually part of the measurement. So, .20 grams. You don't need to show a zero after the decimal place unless it's part of the value of the measurement. So you know that this zero has to be significant. So that is really part of what this rule means. Okay? It's kind of like if you have a useless zero, you can be certain that it's part of the measurement if it's included. So non-zero, non-zero, trailing zero after the decimal place. So this guy has 3 significant figures. Oops. Oh, come on, focus, focus, focus. There we go. Likewise, this zero doesn't really have any purpose there. It's not necessary to show the size of the measurement. 32 is 32 regardless of the presence of that zero. Therefore, significant, 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 3 sig figs. Now we're going to get to a rule that bugs the ever-loving crap out of me. It's one I don't particularly care for, but it's one we are kind of stuck with. Either way, what we're looking at here is 320 grams. Let me be consistent with my zeros. All right, 320 grams either way. This one does not have a decimal place. This one does. Significant, significant, trailing zero, but no decimal place. That is not a significant zero. This 320 only has 2 significant figures. But here we have a number, a trailing zero with a decimal place. This measurement has 3 significant figures. The reason I hate this is because it's literally just a dot. An unnecessary decimal place is how you signify that this number ends with a significant zero. It's the smallest unit of punctuation. It's something that can be messed up by dirt. Okay. But it's the tool that we have. So it is something that they will expect you to know. It's something that is going to show up at the very least on the first test. I expect it to show up on the first test the week of September 7th, the lecture test, and I kind of expect it to show up on the lab test too in the middle of the semester. Okay, this is absolutely something they will test you on. It's annoying. I hate it. I don't think we'll ever get rid of it. Now we can connect significant figures back in, excuse me, with exponential notation. Because exponential notation or scientific notation has a huge advantage in that you never have to worry about significant figures. Because what if we had something like this, 32,000 grams, and we wanted to show that this and this and this are significant, but not these two trailing zeros. Under the normal rules of significant figures, decimals or not, there would be no way to distinguish that zero as significant from those two non-significant zeros. But scientific notation gives us exactly the method we need. Okay, so we have our non-existent decimal. We move it 1, 2, 3, 4 places to the left. And in scientific notation, we have 3.20 times 10 to the 4th grams. And now, this trailing zero is to the right of the decimal place. So by regular scientific notation rules, sig fig rules, those three are all significant figures, and it makes it really simple, really straightforward. Under scientific notation, every single number you see is a significant figure because, like I said before, this is the value of the measurement. And that's what significant figures are intended to tell us. Which parts of the number are part of the value of the measurement, as opposed to this right here being the size or magnitude of the measurement. Okay? So that is what sig figs are intended to distinguish for us. And that is one of the great things about scientific notation. All the digits in the actual number are going to be significant. So now that we've talked about whether or not numbers are significant or are not significant, let's talk about significant math. So what significant figures do for us is they tell us let's see how to put it. It goes with error. Okay? Every measurement you make is going to have some amount of uncertainty, some amount of fuzz. There's no such thing as a perfect measurement. I mean, unless you are counting a very small number of objects, you can't get a perfect measurement. There's always going to be some uncertainty, a little bit of wiggle room at the very, very end. Okay? So that's why when you take a measurement, on a ruler, you're always going to estimate between the lines for the very last decimal place. So say this is 0 inches and 1 inch, and then you have 0.1, 0.2, 0.3, 0.4. This measurement looks to be 0.44 inches. You always estimate. So there's always a little bit of uncertainty there in that last digit, in the last decimal place. And significant figures tell us a lot about that because it tells us that this measurement has two significant figures. And that matters when it comes to doing math. Because the uncertainty in one measurement will have an impact on the uncertainty in another measurement when you start adding, subtracting, multiplying, or dividing. And because addition and subtraction, excuse me, getting kind of thirsty with all the talking. Caffeinated beverage. All right. And because addition and subtraction are slightly different mathematical operations from multiplication and division, they have slightly different rules. Okay. So addition and subtraction, whenever you add or subtract something, it always has to have the same unit. Okay, that is kind of an important bit of information to include in there. So let's say you take a couple of different length measurements. Okay, I measure the length of my driveway using, a meter stick, and I find that my driveway is 25.037 meters long. My meter stick goes down to the centimeter, and then I estimate in between the centimeter lines. Huzzah. Okay. And then I measure the distance from the end of my driveway to the school using the odometer on my car, and I find out that that is, let's go with 25.037 kilometers. It's a really awesome odometer. Kind of ridiculous. So before we can add these together to find out how far it is from my door to the school, we have to get these in the same units. Okay? So let's go ahead and convert this from kilometers to meters. The kilometer is, 1 kilometer equals 10 to the third meters. So we're going to a smaller unit. The number is going to get bigger. So it is 25,037 meters. So now we add 25,037 meters to 25.037 meters. So when it comes to significant figures for addition and subtraction, first, just go ahead, add or subtract as normal. So we add these together. 7, 3, 0, 2, 1, 6, 0, 5, 2. But here's the thing. This measurement here was a lot more precise than this measurement here. Okay? For the measurement of my driveway, my uncertainty is located there in the millimeter range, because my meter stick went down to the centimeter, and then I estimated the number of millimeters. But for this measurement here, my car's odometer only measured down to the meter, and that is where the uncertainty is in this guy. So it doesn't really matter that this measurement was a heck of a lot more precise. The uncertainty in this measurement basically completely wipes it out. So that means that the cutoff is going to be there. Okay? You just, for addition and subtraction, you start at the left and you go, one digit to the right, step by step. Hello, puppy dog. And you go step by step from left to right until one of your numbers runs out of significant figures. So this measurement runs out at the meters place. This one runs out at the millimeters. So our cutoff is going to be right here, which means that this number here is also going to be cut off at the meters. Okay? Which means that you then round as normal, using normal rounding rules, and our actual answer is 25,062 meters, or 25.062 kilometers. Okay? So in a sense, we lost some information. We lost the centimeters and millimeters that were measured in the driveway. And we had to, because this number here could have been anywhere from 25,036.5 to 25,037.4. Hundreds of millimeters, tens of centimeters. This precision is just completely lost by the imprecision of that measurement. So that is one of the ways that we use significant figures. Always take into account significant figures when you're doing math in lab or on tests. Okay. Multiplication and division uses a slightly different set of rules. Okay. So for multiplication and division, multiplication and division doesn't have to have the same units, and the answer will not be in the same units. Okay? For example, if you measure two lengths and multiply them together, you're going to have an area. It's an entirely different kind of measurement. If you measure a mass and a volume, you divide those, you're going to get a density, a completely different kind of measurement. Hence, the rules for significant figures are going to be entirely different. Okay? It's just something that you should expect. So, let's say you weigh something and you find that it weighs 19.03 grams, and you measure the volume of the thing and you find it is 2.57 cubic centimeters. Okay. So here we have a measure of mass, here we have a measure of volume. So for multiplication and division, it's not about the decimal place. It can't be about the decimal place. You're not looking at the same kind of unit. Okay, it's apples and oranges. Therefore, instead, what matters is the total number of significant figures for each of your measurements. Okay, so here we have 3 non-zero numbers and a captive 0. So that is 4 sig figs. Here we have 3 non-zero numbers. So that is 3 sig figs. Now, just as when you're looking at addition and subtraction, your answer is limited by the imprecision of your less precise number, you get much the same thing when you're doing multiplication and division. Okay? The fact is that this number has less information than this number. Or sorry, this measurement has less information than this measurement. This measurement has 4 significant figures worth of information. This one has 3 significant figures worth of information. Okay? So your answer is going to have 3 sig figs. So when you're doing multiplication and division, you count the sig figs. Whatever number has the fewest sig figs, that's how many significant figures your answer will have. So in order to find density, density is equal to mass over volume. So what we're looking at is 19.03 divided by 2.57. I'm not actually going to do that, and now I'm going to thank my cat for trying to sleep on the keyboard earlier because he opened up the calculator for me. So let's see, that's 19.03 divided by 2.57, giving us 7.40466926607. It just keeps on going. All right. So here our answer is going to have as many sig figs as the fewest. So we're going to limit it to 3 significant figures. And as before, we're going to have to round. So our answer is going to be 7.40 grams per cubic centimeter. Don't forget your units. Units are important. Without units, a number doesn't tell you something. It's not a measurement. It's just a random number. Okay? 7.40 what? 7.40 grams in every cubic centimeter of space. Okay? Density is the measure of how much matter fits into space. Okay? All right. So really quick, the rules for rounding. My cat loves to help. He is a sweetheart, aren't you just? And he is the prettiest kitty. You have no idea. All right, so you can see that at the moment. So if the number you're dropping is less than 5, you round down. If it's greater than 5, you round up. If it's equal to 5, things get weird. The reason it's weird is because humans are bad at taking measurements. Statisticians have looked at the way we measure things, and they have come to the realization that we're just kind of crap at numbers, and we don't pick numbers at random, and we don't pick real numbers. Instead, we tend to round automatically. We tend to choose a random 5. So if the number you're dropping is equal to 5, then you round it to an even number. Okay. So for example, 0.45, we would round that to 0.4. 0.35, you would round that to 0.4. Okay. So an even number stays even, an odd number gets rounded up. Okay, so sometimes you round down on a 5, sometimes you round up on a 5. And that is the way statisticians have figured out to take into account the fact that humans and their stupid pudding brains are not all that great at taking measurements. Okay, let's see. What else do we have to look at? Significant figures, significant figure math, scientific notation, dimensional analysis. Can't forget dimensional analysis. All right. Dimensional analysis is just basically if you are doing math. Yeah, it is. And it's something that trips a lot of people up. Second tallest there. But it's necessary for, good science. And you want to do good science, because otherwise you're doing bad science, and that's how you get monsters. And then the monsters take over the earth, and we don't have pretty people anymore. We just have monsters. All right. So now I distracted myself. What was I going to talk about? Oh, yes, dimensional analysis. Basically, dimensional analysis is a way to help with problem solving, to look at the information you have and try to get to the information you want. So gold has a density of 19.3 grams per cubic centimeter. Okay. If you have a rod that is 1 centimeter in diameter that weighs 50.5 grams, how long is it? So, a rod is a cylinder, and I don't know if you remember from various kinds of math classes, the volume of a cylinder is pi r squared h, just the area of the base multiplied by the height of the cylinder. A rod is just a cylinder lying on its side, so it's pi r squared times the length. Huzzah. So we know that it has a 1 centimeter diameter. The diameter is just twice the radius. So the radius is equal to 0.5 centimeters. And up here, I gave you the density, and density is equal to mass over volume. So we have the density, mass over volume. Volume is pi r squared L. We have density we have mass, we have r, we're looking for length. That is kind of complicated, kind of weird. Does it even make sense? Well, yeah, because the units of mass are in grams. The units that I gave you for the radius are in centimeters. When you square that, you're going to have centimeters squared, and the units of length are also going to be centimeters. So on the right, we'd have grams per cubic centimeter, and the density is measured also in grams per cubic centimeter. Okay. So that is one way of looking at dimensional analysis. A dimension is just the unit of a measurement. It's not another plane of existence that you can travel to if you turn sunwise twice and widdershins thrice under the light of a full moon while wielding an empowered crystal. It's just a unit. That's all, a unit of measurement. So another way of looking at dimensional analysis or unit analysis, factor conversion, unit conversion, is when you are doing a conversion from one kind of unit to another. Like take the fastest vehicle that we ever made, the heliotrope orbiter. We sent it hurtling toward the sun, and it ended up going about 50,000 kilometers per hour. The distance from Earth to our nearest star is, let's see, it is about 4.3 light years. So how long will it take for or how long would it take the heliotrope orbiter to get to Alpha Centauri? Or Proxima Centauri. 1 light year equals the distance light can travel in 1 year. So that is, let's see, 12 million miles per minute times the minutes in a year. Yes. Okay. So in order to find out how long it would take for this guy to get through 4 light years, well, we would just compare the units. Oh dear, I did this in miles per minute. Let's say instead it's 180,000 kilometers per second. All right, that's much better. Now our units are matching up. So that's the speed of light. This is the speed of our doohickey. So how long is a light year in kilometers? Okay. Well, light travels 180,000 kilometers per second times 1 year. Well, that doesn't do us any good. We need to get rid of years. Well, there are 365 days in 1 year. Okay. So that means that years cancel out. 2 divided by 2 equals 1. Year divided by year is equal to 1. The units cancel out. But that still doesn't get us where we need to go. So we multiply by 24 hours in a day. Now our days have canceled out. Still not quite there. There are 60 minutes in an hour. So now our hours have canceled out. Not quite done. 60 seconds in a minute. And that will do it. Okay? Because now we have, oops, it's hard to see, seconds on the bottom up here and seconds on the top down there. Now our seconds will cancel out and we'll have converted from a light year into a kilometer. Okay. So 1 light year is 180,000 kilometers per second times 365 times 24 times 60 times 60. And it's going to end up being a fairly large number just because light travels really, really, really darn fast. So 180,000 times 365 times 24 times 60 times 60 gets us 5.6 times 10 to the 4 to 3, 4, 6, 7, 9, 10, 11, 12. Sorry, it's 5.7. I'm no good at rounding. 5.7 times 10 to the 12th kilometers. Notice that I maintained 2 sig figs up there, 2 sig figs down there. All right, we don't have to worry about the sig figs in these numbers here because those are exact conversions. They have infinite numbers of sig figs. Yes, Cupperl, you will be able to find this after I finish. It will automatically be saved to this YouTube channel. And if you can't hear me, yep, microphone is still working. You probably have something muted. Okay. All right. Where was I? Okay, so that is the length of a light year. So there are 4.3 of them in between here and Proxima Centauri. So we multiply that by 4.3 to get the distance to Proxima Centauri. And that gets us 2.4 times 10 to the 13th kilometers to Earth's nearest neighbor. Well, technically to Sol's nearest neighbor. So in order to find out how, it doesn't help to explain to you that yes, you will be able to find this if you can't hear it. If you can't hear me saying that you'll be able to find it, I'm sorry. Thank you, Flying Ponies. I'm a dinkus. I'm going to go ahead and type it in. Yes, it will auto save to channel. Thank you, Pear. Oh, I'm a doof. All right. So we have 2.4 times 10 to the 13th kilometers, and we have 50,000 kilometers per hour. What math do we need to do in order to find out how long it's going to take? Well, we have to look at, oh dear, I am very nervous about you being back there, cat. If this turns off, it's because my cat stepped on the power button on my surge protector. Okay, so we have kilometers per hour. We need to get hours by themselves, which means we need kilometers to cancel out. Okay, so the way you do that, well, I say flip this guy over. Okay. We need hours to be on top, so that is easy enough to do. 50,000 kilometers per hour is another way of saying that when the heliotrope orbiter travels, it travels 1 hour per 50,000 kilometers. Okay, pretty much the exact same thing. Okay, and then we have our 2.4 times 10 to the 13th kilometers to the nearest star. So we hop back over to the calculator, and we find that it's going to, or it would take 488,177 488,177,280 hours. But once again, we have our sig figs. So 4.9 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 hours, which is a very large number of hours. I hope you'll forgive me. Let's go ahead, divide that by 24, divide that by 365.25, take into account leap years. Go ahead and do the conversion super duper quick, and that is 57,000 years, or about 9 1/2 times all of recorded human history. That is how long it would take the fastest ever developed vehicle to travel to the nearest star. 57,000 years. So that is one way of looking at dimensional analysis, is just look at the units you have, play with them until they get you to the units you need. Don't just randomly throw them around, but yeah, it is possible to play with numbers. Remember that when you have something like kilometers per hour, you can think of that as a kind of ratio. 50,000 kilometers per hour is also 1 hour per every 50,000 kilometers. So that's one way to think about numbers. Or to put it back in terms of gold, remember gold had a density of 19.3 grams per cubic centimeter. That means that there are 19.3 grams of gold matter in every single cubic centimeter of gold space. Or to put it another way, 1 cubic centimeter of gold contains 19.3 grams of gold. Okay, just be willing to flip numbers around. Okay? That's basically all division is flipping numbers around like that. Okay? If you're willing to play with things like that, it helps a lot. Now, something that often trips people up when it comes to dealing with units and conversions. Not exactly a special case, but I'm going to go ahead and talk about it specifically. Let's see, 1 liter is equal to 1 cubic decimeter. Okay, just by definition. Remember, deci means 10 to the negative 1. Okay, so 1/10 of a meter is a decimeter. So a cubic decimeter, it's not 1/10 of a cubic meter. Okay. So 1 liter, one way of thinking about it is you have a cube that is 10 centimeters on a side, or 1 decimeter, because 1 decimeter is equal to 10 centimeters. But how many liters are there in 1 cubic meter? Okay. It's not 10. Okay. I'm just going to go ahead and tell you that right now. Because 1 liter equals 1 cubic decimeter. If you want to do the conversion from cubic decimeters to cubic meters, well, 10 decimeters is equal to 1 meter. Okay? So if you were to cube that, you would also have to cube the number. Okay? So, because you can't just cube part of the measurement, you have to cube the whole thing. So that means that 1,000 cubic decimeters is equal to 1 cubic meter. So that's why we make it a point to talk about this specifically. Because 1 liter is equal to 1 cubic decimeter. Therefore, 1 cubic meter has 1,000 cubic decimeters, or 1,000 liters. Okay? Because when you cube the unit, you also cube the conversion factor. So that is something that can trip a lot of people up. Let's see if I can come up with... No, I can't really come up with examples that don't involve area or volume. So I'll just keep on going with area and volume. So, for example, something measures 25.0 centimeters by 15.0 centimeters. That's a 5. What is the area in square meters? Okay. Oops. So the area in square centimeters would be just 25.0 times 15.0. 15 times 25 would be equal to 375 square centimeters. But now let's go ahead and convert that to square meters. 375 square centimeters times our basic conversion factor. We know that 1 meter is equal to 100 centimeters. Okay? But we're not dealing with basic centimeters, we're dealing with square centimeters, so we have to square the conversion. So having done that, our answer, we don't just move the decimal place twice, we move it 4 times, 0.0375 square meters. Okay? It makes it look much, much smaller. Okay? But you'll realize that that makes sense because when we're doing the measurement up here, centimeters by centimeters, if we want to convert to square meters, we can start before we find the area. We could have 0.250 meters times 0.150 meters. And thus we should expect the answer to end up being quite small like that. So remember, don't just look at the unit, pay attention to whether the unit has any exponents, because that will change the size of the number, the size of the conversion that you're looking at. All right, and that is everything. I think, yes, that is everything that they talk about in this lab. There will also possibly at some point be the expectation that you convert between the international system and the imperial system. That's just a regular sort of conversion. So, for example, there are 2.54 centimeters in 1 inch. So 3.5 inches is how many centimeters? You just multiply by 2.54 centimeters per inch. They don't expect you to memorize conversion factors to go in between English or imperial and metric, just because it's a real pain in the ass. So instead, if they were to ask you that on a test, they would give you that conversion factor. I don't know whether or not they will. That's kind of up in the air. Okay, and that is everything for this particular lab. Don't forget that this lab is due Sunday at 8 p.m. So if you have any questions, go ahead and fire them off for me now. Better make it quick. My cat has just walked behind the monitors again. He's eyeing... No, he's heard me talking. He knows I'm talking about him. The Pearson issue. We've hit the limit of my troubleshooting knowledge on that one. It's just, you're going to have to talk to their troubleshooting person. I sent out another communication there. There's a handout attached to that particular announcement. At the bottom of that handout, if you still can't get into Pearson, there is a link to their tech support, and you're going to have to go through them. Because at that point, some people have managed to get in, which indicates that it is a tick issue having to do, I don't know particularly what, but you're going to have to go through Pearson's tech support in order for that to work. Sorry about that, Lillian. Assignments due. Technically, there is the introductory assignment, but that is a 0-point assignment. Its purpose is to get you familiar with the MyLabs thing. And yes, Flying Ponies, completing the lab counts as attendance for the week. So no, Lillian, there's nothing due. It's only technically due, but it's a 0 point assignment. It won't hurt you if you miss it. Hopefully, we can get all the Pearson stuff ironed out. The first real assignment is due on Tuesday of next week. I don't know what you mean by module. The uploading stuff is done through course content. There should be a thing. Let's see. Yes, if you click on yes. If you go to course content, you go down, you click on week 1 lab thing. There's the huge long thing where it walks through again all of this stuff and has a couple more YouTube videos. At the very bottom it says experiment 1 lab report worksheet submission. You download the attached file, you fill it in, then you click on the thing where it says experiment 1 lab report worksheet submission, and it brings up the thing that lets you submit that. Um, 520 nanograms per microliter to milligrams per deciliter. All right, that is actually an excellent thing for unit conversion. Okay, so you're doing it's per microliter. You're doing 2 separate conversions. You don't need a course code, John. The link from Blackboard should be enough. So that's one of the tech issues. All right, nanograms per microliter to milligrams per deciliter. Okay. So you're doing 2 separate conversions there. So you need to convert from nanograms to milligrams. So you have milligrams on top, nanograms on the bottom. Okay, so we're going back to the thing. Nano means 10 to the negative 9th. Then you have micro at 10 to the negative 6th. Then we have milli at 10 to the negative 3rd. Centi is 10 to the negative 2nd. And deci at 10 to the negative 1st. Yes, that's correct, Bear. It's due Sunday by 8 p.m. Okay. So to convert from nanogram to milligram, you need 10 to the 9th versus 10 to the 3rd, or negative 9th versus negative 3rd. There are going to be a million of one thing for every one of the other. Milli is larger than nano, which means that for every 1 milligram, you're going to have 1 million, or 10 to the 6th, nanograms. And you do a similar conversion to go from microliters to deciliters. You just look at the exponents, and that tells you how many of the smaller thing there are in the bigger thing. Okay. So I'll leave that as an exercise for the viewer. How many microliters are there in a single deciliter? So that is how that particular problem is working out. It's doing 2 conversions at once, more or less. Oh, I wrote that kind of small. I'll make it bigger. That is a 6. Oh, the angle made that weird. Oh, darn. All right. At this point, I have been talking for over... the link to Pearson in Blackboard, that's under course content, John. Mastering Chemistry Pierce for regular Chem 110015. Yes. It's the same material, but obviously it's going to take you to a different web page, different set of the same content. Yeah, basically a mirror. Yeah. Yes, ponies. Same content, different location. All right. I know the piercing stuff is frustrating. It's really frustrating on our end too. If for no other reason than that I have to deal with 125 people asking me about this. All right. But as it is, I am dried out, and it is supper time. So I am going to go ahead and call it for the day. And I will catch up with you guys at a later time. So I will see you around. That's a thumbs up. There, thumbs up.